Let's continue our discussion of random variables by considering another type of function that is going to be very useful for our analysis. That goes by the name of the distribution function. Okay. So how do you define the distribution function? For any random variable x and for any x values in the real space, we define a function, this time capital F instead of lowercase f, such that that function of x, that capital F of x, the distribution function, is going to be giving us the probability that the random variable is going to take values that are less or equal to that particular materialization of x. Notice here, notation-wise, this is lowercase x that reflects a particular value that x can take in the space of real numbers, right? And that is this corresponding x over here. So that is the probability that the random variable takes values less or equal than that specific value x over here. Fantastic. Theoretically, x ranges from -infinity to infinity, but then think about the mapping that is happening in this function. So the mapping is from this space of -infinity to infinity, space of real numbers, to the set of 0 to 1, okay? Including the value of 0 and also inclusive of the value of 1. This function, capital F of x, is going to be called the distribution function of x, or even better, for those of you who want to connect to the concept a little bit better, we're going to be talking about the cumulative distribution function, also abbreviated as the CDF of x. Cumulative, why do we talk about the cumulative function? Because essentially what this function is doing is it is accumulating probabilities that is picking up from the PDF or a PMF, depending on whether you're talking about continuous or discrete random variables, and it is accumulating these probabilities into a function. So essentially you're thinking about, well, what is the probability up to that particular value of x? Well, you have a specific probability accumulated. Then what if you increase x by a little bit? Then the probability is going to be higher, it's going to be non-declining. So essentially you're going from a probability of 0 for, let's say, very low values of x to a probability of 1 as the values of x here increase. Let's look at definitions a little bit and some examples. First, we're going to think about the case where x is discrete. How are we going to define that? So this is simply what we've seen so far. Capital F of lowercase x is equal to the probability that your random variable is less or equal to that specific value, lowercase x. How do you get that in the discrete case? Well, you're summing up all of the values of your PMF, right, for all of these cases where s is less or equal to that value x that you're going to try to calculate the CDF for. Okay, so this is going to be much clearer when we talk about the specific example. And here is something that we have perhaps seen before, but this could apply for any PMF that you or PF that you want to establish, any type of experiment that generates that type of a distribution, a probability mass function in particular. So you have the materializations of the x random variable that could be 0, 1, 2, or 3, and this particular row is going to give you values of the lowercase f of x, right? That's your probability function. That in the discrete case signifies the actual probability that you're going to get one of these outcomes, right? So that's the correspondence here. From this piece of information, we can derive the CDF, right? And the way that you're going to be doing that is you're going to be accumulating this probability as the value of x increases. So you can start by thinking about your cumulative distribution function when x is less than 0. In this particular case, this is not defined. That's actually 0 for any other values that are not part of the sample space. In, let's say, the case of, well, x hitting the value of 0, you can start accumulating that amount of probability, 1/4. That's the 25% probability that becomes part of your cumulative distribution function, right? Up to the point where you are going to think about hitting a value of 1, but you're not there yet. But once x takes the value of 1, you accumulate 1/8 on top of 1/4, right? So that's going to be 2/8 plus 1/8. That's going to be 3/8 total. Okay, and you can continue on up to the point of 2, but not equal to 2. Once x hits the value of 2, you can accumulate also this 50% of the probability. That gets you to 7/8. And eventually, once you hit 3, you have summed up all of these probabilities, and we know by definition that this is going to simply be equal. The sum of these is going to be equal to 1, because that's the property of your lowercase f of x. So this functional form, the capital F of x, can be represented as a step function. Also, the way that I showed it to you, you have to be a little bit careful how you draw this. Obviously, even though sort of your x, a random variable, takes discrete values, you can represent space as continuous. You have to think about what points here are open, which ones are closed, essentially at which points you add the probabilities, right? So these are the closed points in the step function. And I think either you think about this in its functional form, or you think about it as a step diagram, and the concept becomes clear. The concept sort of accumulating probabilities. A couple of notes to think about. If x is a discrete random variable, as I said, this capital F can be represented as a step function. F will have, the capital F, the cumulative distribution function, will have jumps at points where you have values for your PF or your PMF, where you have these positive probabilities. Otherwise, the level of probability is not going to be changing sort of between these x values. So F would be remaining constant for those intervals. The next example has to do with, the next definition actually, an example has to do with a case where x is actually continuous. In that case, for this random variable, for a continuous random variable, the CDF is going to be defined very similarly. Instead of a summation sign, we are going to be seeing an integral. So again, definitional stuff, capital F of x is equal to the probability that your random variable x is less or equal than a specific value of x. Well, how do you get that in the continuous case? Well, it is a summation. It's a continuous summation from minus infinity up to that point x, right, where we want to identify the cumulative probability, the cumulative distribution function, or rather the cumulative probability up to that point of x. How do you do that? Well, it's the integral from minus infinity to that point x of f of t dt. Now, notice here something that relates to notation. I could not have used f of x dx as a formulation of what's inside the integral, simply because I want to calculate the value up to that point x, right? So essentially think about it as you are going to solve this integral, that x is going to come back into this expression, right? So it's going to appear over here, and thus I will have a cumulative distribution function that is a function of x. It doesn't matter what I call this variable. We have the definition of the PDF being f of x, but instead of x, you can write here t, you can write s, you can give a different sort of variable name. It doesn't matter. What is actually happening is, as you are making this calculation, or as you're calculating this integral, that x value, that is your upper cutoff point, is going to show up in here. And that is going to allow this probability, this cumulative distribution function, to become a function of x. So that's something worthwhile to remember. You'll see how that plays out in a specific example. And always note that the lowercase f here is the PDF of the random variable x. Capital signifies the CDF. So let's go back to our standard example of the negative exponential and see how this is going to play out. So first of all, take a look. This is going to be the f of x that we're going to incorporate here in this integral, and we're going to change the notation a little bit so that we adjust it accordingly and sort of operate only on the basis of the interval for which we have a definition of a PDF. Let's see how that is going to work out. So the question here is, what is the cumulative distribution function given that you have this particular form of the PDF? So for this example, here's a way to think about the solution. If x takes values, or for x values less than 0, you're simply integrating the function of 0, the PDF is equal, your f lowercase of x is equal to 0. So that leads to your cumulative distribution function taking the value of 0. That's fine. There's no probability accumulated for lower values than 0. So what is actually though happening when x takes positive values, greater or equal to 0, to be more specific, and in some ways that equality sign here does not really matter for the overall calculation, as we've seen before when we've discussed probability PDFs. So here's the integral calculation that we need to make from 0 to x, so that x comes back into this expression as you're working your integration. What is the functional form of the PDF? 1 over 3 e to the power of minus t divided by 3 dt. I simply changed the variable here. Instead of writing x, writing t. That will allow x to come back in. So a few things to consider here, some mental notes in order to think about how to solve this integration problem, how to calculate this particular integral. What we need to do in here is to get this expression to a format that we can more easily integrate, right? So e to the power of x, e to the power of v, as I'm going to write it in this particular example, is a format that we can work with. Essentially apply the endpoints, the cutoff points to that particular form. So that's the goal. How do you get to that? One way, or the starting point, would be to rename this minus t over 3. So if you call this v, and I do this in a little bubble, so this is the way that we're going to think about going from this to this step, right? So if I call this v equal to minus t over 3, I can think about the differential for this expression, or simply do the derivative. Dv over dt is equal to minus 1 over 3. Fantastic. This is something that I'm also going to use because I have a dt value over here that I want to express in terms of this new variable v. The other thing that is going to be important to think about is how the endpoints for the integral are going to change. The lower one does not change at all. When your t variable is equal to 0, this is going to be 0 divided by 3, so that's a 0 value. So this does not change in terms of the v variable, but this is going to change. So when your t variable takes the value of x, okay, we go back here into our little bubble. T variable takes the value of x, that's going to be minus x over 3. So that's how that upper cutoff point for the integral changes. So everything here has been expressed in terms of this new v variable. The other thing that I did not mention is we had 1 over 3 dt over here. We needed a minus sign to make this a dv. So we add the minus sign in front, and so we can have that differential over expressed in terms of the v variable. Okay, so this is something that we can work with, and you've done these types of integrals before. So this is a minus, this gets carried, of ev evaluated at minus x over 3 and at 0. That's something that you can do a very simple substitution for. So minus e to the minus x over 3, okay, minus this expression again where the v value is 0 here. So minus the minus of e to the power of 0. Fantastic. So when you do that calculation, that is equal to 1. That minus times minus becomes a positive sign, minus e to the minus x over 3. So that is the expression for the cumulative distribution function. So 0 if x values are less than 0, and 1 minus e to the minus x over 3 for positive values of x. So you have found the functional form. How can you use this functional form to calculate probabilities? Well, you simply substitute or pick a value of x in this functional form. You substitute it in here, and you make the calculation, and you derive the relevant probability. So for example, what is the probability that your random variable x is less or equal than lowercase x? Let's say for the specific case where that lowercase x is equal to 2. That can be rewritten as the probability of x less or equal than 2, or you can rewrite this as f, capital F of 2. That is equal to this 1 minus e to the minus 2 over 3. You take your calculator, you figure out what that particular probability value is. Remember, the mapping suggests a mapping from the space of real numbers to the interval between 0 and 1. So in order for this to be a cumulative probability, it has to range between 0 and 1. So if you find values here that are over 1 or less than 0, there has been some mistake that has happened in the calculation. So we have a variety of properties for the distribution function that are important to be aware of, and most of them are very intuitive. First of all, the capital F of x, the CDF, is non-decreasing. That means for lower values of x's, let's say x1, which is less or equal than x2, we're going to have a capital F of x1 being less or equal than capital F of x2. That should make a lot of sense to all of you, because as we are progressively increasing x, we are accumulating probability from the probability mass function, or the density function, is something that is always going to be the case. Property number 2 has to do with how these functions behave as you're approaching, as x approaches infinity. So the limit of this cumulative distribution function is going to be equal to 0 as x approaches to minus infinity, and the limit of the f of x is going to be 1 as x approaches positive infinity. And note that the function is less or equal to 1 for every x in the space of real numbers. Another property that relates primarily to discrete distributions has to do with the fact that f of x is going to be defined as right continuous. In order to get into the discussion of right continuity, you have to be aware of some definitions, essentially defining g of x superscript plus sign. That is the limit of this function g of y as y approaches x from larger values, right? So y being larger than y, that's also referred to as the right-hand limit, and g of x superscript a minus sign being the limit of this function g of y as y approaches x from smaller values, right? So you can think of this as diagrammatically, given the two diagrams here. In calculus, we use these concepts to describe the continuity of a function, right? So at point x naught, if this g function of x naught plus is equal to the value of the function for x naught minus is equal to simply the value of the function at x naught. So the limit as you're approaching x naught from positive, from larger values, the limit as you're approaching x naught from lower values, smaller values, being equal to the actual sort of value of the function at x naught. That defines sort of continuity. So a function g of x formally is right continuous. That is the property of the CDF at that particular x value if essentially the g of x plus is equal to the g of x. Visually, you're trying to figure out at a particular value of x whether the value of g is open as you're approaching x from lower values, from smaller values, or whether that particular point is closed as you're approaching the point x from smaller values. So similarly to the example that we saw before, the step function, right continuity means that as you're approaching this value x from larger values of x, that's where you want to see the closed point. Another very important property has to do with how you calculate a different type of a probability rather than the one we have defined for the cumulative distribution function. So how about defining the probability that x is simply greater than a value of x? Well, this is an easy thing to do because we know that probabilities are constrained between the values of 0 and 1. So this is simply going to be 1 minus the value that you get from the CDF, right? 1 minus the CDF generated probability, right? This is the definition of the CDF. So that would be simply 1 minus the capital of f of x. That's quite useful because in many problems we're not going to simply need the probability that x is less or equal than x. We're going to need the probability that x is greater than a specific value of x. Simply 1 minus the value of the CDF is going to give you that probability. And the other point being the point in the continuous case of whether sort of these inequalities matter and how you sort of process that information. So simply expanding on property number 4, property 5 says, well, you can use the information that you have available already to identify the probability that your random variable x takes values between two specific materializations of x. More generally, in the more general case, you can establish that the probability that x is less or equal than x2, a higher value of x, and simply greater than x1, which is a lower value of x, is going to be equal to the difference of the two CDF values. The probability that random variable x is greater or equal than x2 minus the probability that your random variable x is less or equal than specific materialization x1. So this is a property that emerges because of the discussion that we just had on the right continuity of the CDF. More generally, in the case of a continuous random variable where those inequalities don't really matter, you can calculate, essentially when you're doing this, you're calculating the probabilities of less or equal, both when it relates to larger values of x or lower values of x. So essentially this is picking up the discussion that we have been having on the idea that a specific number does not accumulate any probability in the case of continuous random variables. So essentially the inequalities do not matter that much. But note that if you do have the discrete case, okay, you cannot simply do that. You need to be careful in the case of discrete random variables. And an example in your notes relates to this particular diagrammatic version of a CDF, where you can start thinking about different types of probabilities and how you calculate them. So for example, given this information that you have available here, how would you go about thinking about the probability that your random variable x takes values of less or equal to 1? So let's look at that. At the point 1, you have the right continuity that we have been discussing. That's fantastic. What is the probability once you have hit the value of your random variable being less or equal to 1? Well, that would be 1/2 in this particular problem. You can continue on applying the properties for CDFs. So what about the probability of x being greater or equal to 2? Okay, you see at 2 you don't have any changes in the levels of probability. The cumulative probability changes once you hit the x value of 3. But over here, you know how to handle this, right? Based on property 4, right? Greater or equal, that would be 1 minus the probability of x is less or equal to 2. That would be 1 minus the value of f2 here is, again, 1/2. 1 minus 1/2 is simply 1/2. So you have an example for calculating this probability too. So a few more calculations of probabilities are going to be available in your notes, and some of them are sort of subject to your own exploration. Perhaps the most important property for CDFs has to do with how you can jump from a functional form that reflects a CDF to a functional form that relates to the corresponding PDF, and vice versa. So The property suggests that for a continuous random variable x, the CDF can be obtained from either the PF or the PD and vice versa. The proof of this is as follows. So on the one hand, if you have a PDF, you can calculate the CDF in the way that we have been seeing up to this point. The probability of x is less or equal than x, being the integral of this CDF from minus infinity up to point x. Alternatively, if you have your CDF being given, the capital F, you can calculate the PDF by simply taking a derivative of this capital F of x with respect to x, and that is simply going to give you your PDF. You don't need to have one or the other for a representation of the probabilities in the particular experiment or in the particular situation that you are describing. You can equally represent a continuous random variable either by using the PDF or PF in the discrete case or the CDF. Okay? You can use the accumulated probabilities or you can use the densities of the probabilities for the description of the processes that you're thinking about through these functions. Alternatively, you can use a distinct notation for the PDF that helps make the point across, right? So d of f of x is sometimes used to denote the PDF, of course, because this is a differentiation of the CDF, right? So this is sort of the exact analogous format. The example here that relates to this property 6 has to do with taking a CDF or having the CDF being given and being asked to find the probability density function for that. This is a rather simple problem because all you have to do in this example is differentiate this capital F of x, take the derivative with respect to x, and establish the finding, and thus you will know that you have identified the PDF. Also, a final note here. This is not a unique function. That's kind of a technicality because of the fact that we're working through continuous random variables. You can assign this equality either on this branch of the function or this branch of the function, or if you had even more branches in the CDF, you would have an equivalently larger set of branches in your lowercase f of x, and because of the type of the variable that we're discussing, it wouldn't necessarily matter where you assign sort of those cutoff points, or rather how do you assign the inequalities across the cutoff points.